So I'm about to tell my daughter a chemistry joke. I'm gonna see if she thinks this is funny as I do. Hey, Lisa. So I was sitting on the subway and I asked the guy sitting next to me. I said, "Hey, do you have any sodium hypobromite?" Do you know what he said? He said, "Nah, bro."
What's up, everybody? Back again with another video. Unfortunately, my daughter didn't find my joke as hilarious as I did. I thought it was pretty funny. I don't know about you guys. All right, so here's what we're going to cover today. We're going to be covering how to predict chemical formulas for ionic compounds. Now, you have to remember, first and foremost, what an ion is. An ion is any element that has lost or gained an electron, right? So typically what we see is in elements that are located on group 1 and 2. If I can get my little pointer here, if I look at elements located in group 1 and 2, these are elements that, for the most part, will give up electrons, right? Something over here in group 1 has typically an oxidation number of +1. Something in group 2 has typically an oxidation number of +2. Now, if you remember why that is because it is interpodically favorable for it to lose 2 electrons rather than it is to gain 6. If you come all the way over here to the other side of the periodic table where you have groups 16 and 17, or 6A and 7A, we find elements that would much rather, or find it interpodically favorable, to gain 2 or 1 electrons. So when we're dealing with ionic compounds, for the most part, we're dealing with elements located in group 1 and 2 and group 6A and 7A, okay, where they're going to be losing and gaining those electrons. All right, so now let's jump into actually predicting chemical formulas for ionic compounds. All right, now for the most part, when I've done this is kind of the strategy I've always done. Now, I will tell you that in the future, as you start getting a little bit better, as with most things in this class, you won't need to go this and you'll just kind of know it right off the top of your head. But there is always that work that needs involved. So the first element that we're going to be working with right now is going to be, if I can bring up my laser pointer, lithium oxide. All right, so my first step in all of this is I'm going to look for lithium on the periodic table and find out what group that it's in. So lithium is in group 1A, which means what? Well, if you remember from before, it means that it has an oxidation number of +1, all right? So that means that it's interpodically favorable for it to lose 1 electron rather than it is to gain 7. The other element here is oxygen, right? Oxygen is located all the way on group 6A or 16, right? Which means that when it becomes an ion, that it's going to gain 2 electrons with an oxidation number of -2. Okay, so what does this all mean? So what this means, in order for it to be interpodically favorable, it's going to have a charge. It's going to form an ion. Lithium, as we discussed before, you rarely ever find in its elemental state out in nature, right? Most of the time, the majority of the time, 99.99% of the time, you will find lithium as an ion because it is more stable that way. It is more interpodically favorable for it to be found as an ion. Okay, so let's jump now into how we predict. So the first thing we're going to do is we're going to write each of these elements in their ionic form. All right. So lithium, as we establish, is going to be found as a positive charge. Positive by how many? According to our oxidation number, positive by 1. So we're just going to put a plus sign up here just like that. Okay. Oxygen, which by the way, when you write ionic compounds, you always write ionic compounds. The anion always comes after the cation. So the cation, the positive charge, always comes first. Then the anion comes second. So here, lithium is our cation, positive. Oxygen is going to be our anion, all right? When you write an ionic compound, you always drop the last part. So it isn't lithium oxygen, it's lithium oxide. You drop the last part of the element and you add IDE, lithium fluoride, lithium oxide, lithium bromide, sulfide, examples like that, okay? All right, and then oxygen, I'll do this in a different color. Oxygen is going to have an oxidation number. I'm going to draw this a little bit further to the side just so you can kind of get a sense of what I'm doing here. It's going to have a 2- charge, which means that it has gained 2 electrons. Remember, when you gain an electron, you become more negative. If you lose an electron, you become more positive because electrons have a negative charge. All right, so I'm going to write the formula down here with no subscripts just yet. Okay, lithium and oxygen. Now, to help in this process, what I'm going to do is I'm going to circle both the numerical charges for both of these ions. Notice that lithium does not have one, but I'm going to circle something here anyways. All right? There is an imaginary number there. Well, it's not imaginary. It actually is there. If we put no number there, we know that the number is 1. I'm going to do the same thing over here with oxygen. Oh, I messed up. Right here, circle the 2 because that's my numerical quantity. And all I'm going to do is I'm going to crisscross the number. 2 is going to come down here to lithium, and 1, which is not there, is going to come down to oxygen. Since there's no number there, I'm not going to write anything. I'm not going to write anything for oxygen, but I am going to write 2 down for lithium. So right here, I'm going to put a 2 right here, and no number behind oxygen. And that's it. That's our chemical formula for lithium oxide. Lithium oxide's formula is Li2O, just like that. All right, so you got to remember, all we're doing is we're crossing the numerical quantities, right? Letting us know that in a single compound of lithium oxide, right, we have 2 lithiums to every 1 oxygen. Now, some of you guys are asking, why is that? Why is it there's 2 lithiums? Well, you have to remember, right, that lithium only has 1 electron to give per atom, right? Or excuse me, one electron to give up per atom, where oxygen needs 2 more electrons to do it, all right? So there's a problem here. So the only way to square this up is that lithium has to find another homie, right? Here's another lithium, here's my oxygen, boop, right? Mighty Morphin Power Rangers, they unite, so on and so forth, and now you have an ionic compound. 2 lithiums for every 1 oxygen that you have, forming our new compound, lithium oxide. All righty? Okay, so let's jump to our next example. Oh, and by the way, I almost forgot. I'm going to understand that when we write these chemical formulas down, what we're actually writing down is what's called our empirical formulas. Our empirical formulas are the lowest possible number of atoms that you can have per compound. Now, sometimes, especially when we write covalent compounds, we don't write empirical formulas. We use what's called molecular formulas. That's the actual number of atoms per compound. But for all ionic compounds, it will always be the empirical formula, which is the least, I can't think of the word off the top of my head, but just know that it's the lowest number possible for that compound, okay? Okay, so let's move on. So now we got sodium fluoride. Once again, I'm going to follow my same procedures. I'm going to find sodium on my periodic table. Once again, sodium is located in group 1, right? Which means that when I go to write this down, it's going to have an oxidation or an ion charge. We know the oxidation number is +1 or +1, which we know, which means that its ionic charge, right, as an ion, is going to be the same thing. So it's going to be sodium with a positive charge just like that. Okay. Now we got to do fluorine. So fluorine is located in group 7A, which means it has 7 valence electron, which means that in order for it to complete its octet, it needs 1 more electron, right? So it's going to gain 1 electron. So as an ion, it's going to form fluorine by -1. So all we do is write a negative there. And as we discussed before, the next thing I'm going to do is I'm going to write down my chemical formula down below. I'm going to do this in purple, right? Sodium and fluorine with no subscripts whatsoever. Remember that the subscripts let us know how many atoms in each of those compounds there are and what the ratio is of those atoms. As we discussed before in the last problem, right, it was a ratio of 2 to 1, right? For this one, it's a little bit different, okay? So we're going to circle the numerical quantities, which in both of these there are none. We're going to bring both of those down. Since they're both 1s, I don't write anything at all. That's why I circled nothing there. There's nothing there for me to write. So the chemical formula, the empirical formula for sodium fluoride is just as it's written right now. It's NaF, right? Sodium fluoride, okay? So that's just an example letting you know what the ratio is when you have a 1-to-1 ratio. There is no number. So that means for every 1 sodium, there is 1 fluorine, sodium fluoride, okay? Now, I will tell you that in the future, I won't let you guys just say NaF. Right, you got to let me know what it is. You'll get it as you go on, right? We really don't cover naming and stuff like that, but because we use these so often, you'll just kind of get used to naming these things. All right, so sodium fluoride is that one right there. All right, so let's jump to our next one. Our next compound is magnesium chloride. So much like we did before, we're going to find magnesium on the periodic table. Magnesium is located in group 2A. Now I'm going to find chlorine. Chlorine is located in group 7A or 17, right? Once again, I'm going to write down their charges. Remember that the oxidation number for something located in group 2A is +2, and something that's located in group 7A is -1. All right, so as ions, what that means is magnesium is going to lose 2 electrons to complete its full outer shell. So here's magnesium, Mg. And by the way, every time you write an ion, you always put the number first and then the charge. It's a little bit different than oxidation numbers, right? Whereas oxidation numbers, you write them as you would typically do in any other sense in a mathematics class or whatever. But in chemistry, when we write ions, we always put the number first, then the charge. Okay, and the next number the next element that we're going to put down is chlorine. As we already established, chlorine is located in group 7A, therefore it has an oxidation number of -1, which is ion charge is going to be 1, negative, or just a negative sign, just like that. Alrighty? Excellent. Next thing we're going to do is we're going to write down our chemical formula. Remember our empirical formula, because it's the lowest ratio possible, of magnesium. There's the word, I figured out. I forgot it again. Lowest ratio possible. Magnesium chloride. As we did before, we're going to circle the numerical values of each of them. Here we got 2. Over here there's a 1, even though there's no number there. Okay? I'm going to crisscross applesauce and bring them down just like so. Right? And I'm going to write the new subscripts there. There's no number for magnesium, so I don't write anything down. There's a number 2 for chlorine, so I write a number 2 down here. All right? So my empirical formula for magnesium chloride is MgCl2. Square it up, let you guys know what I have. So what that means, once again, is that for every 1 atom of magnesium, there are 2 chlorine atoms. Okay? Now, once again, because I want to make sure that you guys understand this, well, why is it that there's 2 chlorines for every 1 magnesium? Remember again that magnesium only needs 1 more electron to complete its outer shell, right? Magnesium, though, happens to want to give up 2 of them, right? It is entropodically favorable for it to give up 2 electrons. So what do? Well, in order for me to square this up, in order for me to give up all the electrons that magnesium needs to give up, it needs 2 chlorines to do that because it needs 2 electron acceptors, right? So not just 1 chlorine, but rather 2. Because remember, if chlorine, is it possible for chlorine to take to the 2 electrons? The answer is no. There's just simply not enough space and not enough energy levels to complete that. So you need another chlorine. All right. If I was going to draw a Lewis dot structure, maybe that'll help out a little bit in this example. I'm going to erase all this stuff here, and I'm going to show you what that might look like at the atomic level. So if I have magnesium, I'll do this in orange so you guys can see a little better. Magnesium has 2 valence electrons. 1, 2. Actually, I'm going to draw these in different colors so you can see a little bit better. This is the reason I had you guys learn Lewis dot structures before, so this makes a little bit more sense to you guys. So I have magnesium, right? I also have chlorine. So chlorine, make this one blue, has how many valence electrons? It has, I want to make these ones greens, it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Now, if you notice, it needs 1 more electron to complete its full outer shell. In other words, it has 1 unpaired electron. Okay, so here's what we're going to do. Magnesium comes around and it wants to give up 2 electrons. So when it gives up those 2 electrons, chlorine can only accept 1 of those electrons. So what do you do with this one right here? Well, it's going to need another chlorine to accept that 1 electron. Cl, once again, 1, 2, well, that's not the way you do it. 1, 2, 3, 4, 5, 6, 7, right? Now, this other electron has somewhere it can go, right there. But because you've done that, remember now, you have a negative charge, and this one has a negative charge now. And since you lost these 2 electrons over here, electrons are all gone. Now magnesium has a charge as well. Now how many electrons did it lose? It lost 2 of them. So it's a 2 plus charge. And that's the reason you have the chemical formula, the empirical formula of magnesium chloride with 2 of them. A ratio of 1 to 2. Okay. Good stuff. All right, now, another easy one. So let's do calcium sulfide. So once again, I'm going to do the same thing I did before. I'm going to find calcium sulfide on my periodic table. Calcium is located in group 2A. Sulfide, or sulfur, is located in group 6A, right? Or 16. So that means that calcium will need or will give up 2 electrons. Sulfur needs 2 more electrons to complete its outer shell, so it's going to gain those 2. This is going to be my cation. This one's going to be my anion. All right. So my cation here, calcium with an oxidation number of 2 positive, or its ion charge of 2 positive. Sulfide has an oxidation number, or sulfur has an oxidation number of 2 negative. I'm going to put this a little bit further to the side so you can see a little bit better. I don't know why it's not erasing. There we go. Oxidation number of -2 with an ion charge of 2 negative. All right, we have our cation and anion. Okay, so I'm going to write my formula down here, calcium sulfide, and I'm going to bring these two numbers down. 2, 2. All right, 2, 2. Now, am I done? The answer is 100% unequivocally no, because if you remember before, I told you guys this is an empirical formula. An empirical formula is the lowest ratio possible. Ca2S2, or calcium sulfide, does it have right now its lowest possible ratio? The answer is no. If it's a 2-to-2 ratio, well, guess what? 2-to-2 is the same as saying 1-to-1. So calcium, the actual empirical formula for calcium sulfide is just as follows. Calcium sulfide, just like that. You get rid of the 2's because, once again, it's a 1-to-1 ratio. All right? This is, I'm telling you right now, that's one of the biggest mistakes that kids make, especially when they're first starting off and predicting chemical formulas. When we start predicting masses and quantities of compounds, this becomes a problem because you need to have, especially when you go to figure out molar mass, it becomes a big problem because now instead of only having 1 calcium and 1 sulfur, right, as the ratio, you actually have 2-to-2, which is not correct. Okay? It is not 2-to-2. It only takes 1 calcium and 1 sulfur to do this. Okay? If we go back and think about our Lewis dot structure, remember that calcium has 2 electrons to give up. Luckily for it, sulfur has 2 that it can accept. So you only need 1 and 1 of each to actually make it work. All right? So there is our chemical formula for calcium sulfide, CAS. Right? When I say it like that, it almost sounds like a reggaeton beat. CAS, CAS, CAS. I've been listening to a lot of reggaeton right now on Apple Music because I've been playing. I don't know the guy's name, but the album's called Colores. It's pretty awesome. It's pretty awesome. Okay, let's go to our next one. Okay, so right here, I have a chart that some of you guys right now you won't have to remember, but if you ever take chemistry in college, if you ever decided to major in any kind of like biology, chemistry, physics, or whatever, at some point you're gonna have a set of professors who are gonna tell you you need to remember this chart. Well, for this class, you don't need to remember it. My AP kids, yeah, they kind of remember it, but is it required? Only some of them, okay? You guys will just remember some of these because you use them so much. Now, let's review real fast what a polyatomic ion is. A polyatomic ion is any ion that has more than 1 element associated with it. So, for example, if we look at one of these polyatomic ions, right, like let's say ammonium, right? Ammonium has nitrogen and 4 hydrogens. When you put them all together, bonded together in a covalent bond, it actually does have a charge, right? It has a charge of +1. You're not going to find any of these on the periodic table. You just have to know what the charges are and what the name is to figure them out. Now, some of these we'll use so often, like for example, nitrate, you will learn by the end of this, phosphate, carbonate, ammonium, sulfate, if I could, already said that one already, and something like hydroxide right here. So you'll have to remember some of these, absolutely. Now, do you have to remember all of these? No, especially when you have polyatomic ions like sulfite and sulfate. The only thing that changes between those two is that sulfate has 4 oxygens and sulfite has 3, okay? Now listen, when you're first doing this and you're in college, it's a pain in the butt. I will always give you this chart, right, if you need it for your work, and you can always reference it if you need to, absolutely, okay? All right, now, here's the thing. Polyatomic ions, right, still form ions, which means they can still form ionic compounds. Because remember, ionic compounds are drawn together through electrostatic forces, opposites attract. Positive, negative, Mr. and Mrs. Dominguez, boom, right together to form a charge. Okay? All right, so let's move on into figuring out how we use these in ionic compounds. Okay, so there's your chart that I'll put in OneNote for you guys so you guys can see it. Right? Oh, don't forget, I'm still going to be posting stuff onto your guys' OneNote, so periodically take a look in there, or I'll just tell you guys, go take a look at your OneNote if there's an assignment. The next assignment we're going to do is an explore activity that you should be able to do from home. Okay? All right, so here's our first ionic compound that incorporates a polyatomic ion, sodium sulfate. Just get in the habit of saying these things. Sodium sulfate. Okay, and it's not sodium sulfide because that would be something different. Okay, so here's my chart that I have. First thing I'm going to do is I'm going to locate sodium on the periodic table. I don't have my periodic table up here, but just know that it's located in group 1, right? Therefore, my ionic charge is just going to be positive 1, just like that. Okay? Now, sulfate, I have to look on my chart. Where is sulfate? So we go to look for it, and sulfate is located right here. If you notice, sulfate is SO4, but its ionic charge is 2 negative. It's 2 negative. So I'm going to write down exactly like it's written right here, SO4, 2 negative. And just like we did before, we're going to follow the same procedures that we used before to actually write down our chemical formulas. All right? So sodium, I'm going to circle the numerical quantity, which there is none there, and I'm going to circle the one that goes over here. So I'll write this in purple, like that, and like that. I'm going to write down my new chemical formula, NaSO4, right? And I'm going to take my numbers down, and I'm going to crisscross applesauce them, just like that. Okay? There's no number for sulfate, so I don't write anything there, but there is one for sodium, so I put a 2 down there. Okay? So my empirical formula for sodium sulfate is Na2SO4. And there you got sodium sulfate predicted 100%. Bing, bang, boom, done. All right? Now, I know what some of you guys are saying. Well, Mrs. Dominguez, it's not the lowest common ratio. Yes, I understand that. It is not the lowest ratio possible. But here's the thing. You have to treat this polyatomic ion, sulfate, as its own element. So you don't mess with it at all. You just leave it as is. All right? Just leave it as is. This doesn't account for the amount of, well, it does count for the amount of atoms in the molecule, but you don't disrupt it. It's sulfate because it's held together covalently. You're not going to break those bonds to reform something else. Okay, so what this means is that for every 1 molecule of sodium sulfate, you have a 2-to-1 ratio. 2 elements of sodium and 1 sulfate ion for each one of those compounds. Okay? All right. Let's move on to the next example. The video is getting a little bit long. So our next example is calcium nitrate. Calcium nitrate. Once again, I'm going to look at my periodic table, and I'm going to look, right, for calcium. Calcium is located in group 2A, right, which means that it has an oxidation number of 2, right, 2 positive. So its ionization number is going to be 2 positive. So I'll write calcium, Ca, 2 positive. Nitrate, I have to look, because once again, it's a polyatomic ion. I'm going to take a look over here. Nitrate's located right there, and it has a -1 charge. So I'm going to write that down. Right now, we got nitrate with the negative charge right there. And I'm going to write down my new chemical formula. So I'm going to write down, let's do it in blue, calcium nitrate. Okay? Now, like I did before, I'm going to circle my numerical values, and I'm going to bring them down. There's no number to bring down for calcium, but there is a 2 to bring down there. So what do? You write a 2 down here. Now, listen, this is important. This 2 applies to the whole polyatomic ion. All right? So how do we do that? Well, we wrap the whole polyatomic ion in parentheses like that. Don't you just feel fancy now that you've done that? Now you learn how to do that. Now you know how to do it, right? So now our new chemical formula, our new empirical formula for calcium nitrate is CaNO3, wrap that sucker in parentheses, and put a 2 at the end. And here's what this means. That in 1 molecule, right, of calcium nitrate, the ratio of calcium to nitrate is 1:2. 1 calcium for every 2 nitrates. Alrighty? So that's how you do, that's how you predict ionic compounds. What I want you guys to do next is a concept check, so you can pause your video right here. All right, and there are the answers for sodium carbonate and magnesium phosphate. See how well you guys did. Hey guys, we'll put more of these video outs for you guys. Hopefully you guys have a wonderful day. I will see you guys later. Peace out.